Hello students, the next experiment is study of dielectric constant and Curie temperature measurement of ferroelectric ceramics. The objective of this experiment is to study the dielectric constant at different temperature and to find the Curie temperature of the ferroelectric ceramics or ferroelectric materials. We know as per the conductivity, materials can be classified into two major categories. One is conductor and the other is insulator. So apart from them there are superconductor, semiconductor, etc. But largely we can divide into conductor and insulator or dielectric. So what is electrical conductor? So electrical conductor are those materials that allows the flow of charge in one or more directions. In that material, the electrons associate with the nucleus that roam around, right? They are free to flow. But in dielectrics, or we call it as insulators, the charges are attached to specific atoms or molecules. They are not free. They are not. They cannot roam around the molecules. Okay, they are attached to some specific atoms and molecules, and this attachment is tight, right? So within the molecule or atom, they can move a little bit, but as a whole, they cannot flow like the conductors. In this experiment, we'll concentrate on the dielectric materials and the dielectric properties of that material. So suppose there is a neutral atom, neutral dielectric atom. Now we are applying an electric field. Okay, then what will happen? The atom as a whole is electrically neutral, right? But there is a positively charged core, that is the nucleus, and surrounding it there is a negatively charged electron cloud, right? So to the negatively charged the centers of the negatively charged electrons and the centers of the positively charged core, these centers coincide in a neutral position, in a neutral situation. Okay, but if the electric field is applied in that material, then these centers will be displaced. Okay, so positively charged nucleus will be pushed in the direction of the field, and negatively charged electron clouds, that will go opposite way. Okay, now there will be two forces here. So one is the electric field that will tend the charge these centers to be dissociated, to be apart, and these two separated charges, the separated centers of the charges, they will tend to attract each other. Okay, so in the mutual attraction and pulling the nucleus and the electrons apart, so these two opposite forces will polarize the atoms. So when these two opposite forces balances each other, then the atoms will itself be polarized. Okay, the plus charge will be shifted slightly in one way and the minus in the other way, like you can see in the picture. Now the atom has a tiny dipole moments, small p vector, which points in the same direction as E. This induced dipole moment. Why it is induced? Because it is due to the external electric field. The dipole moments is generated due to the external electric field. That's why it is induced. So this induced dipole moment is proportional to the field. So we can say that small p vector is equal to alpha E, where E alpha is called polarizability. Okay, and it is the material dependent property. It depends on the structure of these atoms. So this proportionality holds only when the field is not too strong. Okay, because if the field is too strong, then it will ionize and it will become a conductor. But as long as the field is low, is weaker, then the polarization will happen, and dipole moments, induced dipole moment, will be proportional to the external electric field, that is E. Okay. Now what is polarization? So polarization is defined as a dipole moment per unit volume. So it is electric dipole moment, and in the magnetic properties, we have already read that magnetization is a dipole moment per unit volume. That was the magnetic dipole moment, but here the polarization is the electric dipole moment per unit volume, and it is also proportional to the field E. So P, that is capital P, that is polarization, can be, we can say that capital P is equal to epsilon naught chi E into capital E vector. Okay, where epsilon 0 is the permittivity at vacuum, and chi is the electric susceptibility, and E is the external magnetic field, external electric field. Again, this proportionality holds only the electric field is not too strong, and the materials which obey these relations are called linear dielectrics. Okay, now here capital E is the total field. So suppose the dielectrics is placed in a external field E0, but we cannot compute capital P directly from the equation P is equal to epsilon 0 chi into E. Why? Because the electric field will polarize the material, and the polarization itself will create a electric field, and that will modify the external field. So it will be a continuous process. Okay, so electric field will change the polarization, and the polarization itself will change the electric field. So that is why we cannot compute the P, capital P, directly from the equation P is equal to epsilon 0 chi E. So we'll introduce here the displacement current. So the displacement current capital D is defined as epsilon 0 E plus P. Okay, and this displacement current capital D, we can get it from the directly from the free charge distribution. So capital D would be epsilon 0 E plus capital P, that is epsilon 0 E, and in place of capital P we can say epsilon 0 chi E into capital E. So if we take the common of epsilon 0 1 plus chi E, so we'll get epsilon 0 1 plus chi E into capital E. So basically capital D, that is the displacement current, is proportional to the external field. Okay, so capital D is equal to epsilon E. So this epsilon is epsilon 0 into 1 plus chi E. This is called the permittivity. Okay, Now if we take in the vacuum, that is the permittivity in the vacuum in the free space, that is permittivity of free space. Okay, and epsilon over epsilon 0, that is permittivity of a material over the permittivity of a free space. If we take the ratio, we will get relative permittivity, that is called dielectric constant of a material. So dielectric constant of a material epsilon r is equal to 1 plus chi is equal to epsilon by epsilon naught. So this is the dielectric constant of a material. If two conductors are separated by dielectrics, it will act as a capacitor, and the capacitance is defined as the charge capital Q over capital V, because capital E, that is the electric field, is proportional to the charge and the proportional to the potential, right? So this proportionality is called capacitance. Okay, so capacitance is dependent on geometrical quantity like the shapes of the material, the size of the material, and the separation between the two conducting probes. Okay, now dielectric constant we can also define as the capacitance of the material, and capacitance using the vacuum as the dielectric. So this ratio, that is C and C0. What is C? C is the capacitance of the material used as the dielectrics in the between the two electric to conducting probes, and C0 is the capacitance of the same size and the same shape to the material. So the capacitance of the vacuum, that is C0 when it is used as a dielectric in the place of the dielectrics, right? So C0 is epsilon 0 into the area, cross-sectional area over the thickness of the sample. So C0 is epsilon 0 capital A over T. Okay, so if the capacitance of the material is known, then by calculating the C0 with the help of the dimensions of these materials, we can get the dielectric constant, as the dielectric constant is C over C0. Now there are some materials which spontaneously acquire the electric dipole moment below a certain temperature, and that material exhibits a hysteresis curve like in the ferromagnetism. Okay, so here the hysteresis curve will be P, capital P, that is polarization versus electric field E. Okay, so these materials are called ferroelectric material or ferroelectrics. So when an electric field is applied to the ferroelectric material, the polarization will rapidly be increased with the increasing electric field, and above and in the above value of electric field it got saturated. Okay, so this dependence of the P and E will be linear, so that linear extrapolation to the P axis will be the saturation polarization. Okay, now initially it was field 0, and if we increase the electric field, it will follow the path OB, and then and it got saturated, and then if we reduce the electric field, then instead of following BAO, it will follow BPR. Okay, and at the point of E is equal to 0, there will be some polarization, some remaining polarization, and the polarization got minimized. It will be 0 at some negative value of E. Okay, and in the negative value of E, if we keep decreasing, there will be some point at which the saturation, the negative saturation will occur. Okay, now if we further increase the electric field, it will uh, it will go to the negative polarization, and ultimately the hysteresis curve we can get. Okay, hysteresis loop we can get. But above the particular temperature, the relation P versus E will be linear. That is, the ferroelectrics will be no longer will show ferroelectric properties. Rather, it will be a paraelectric material. It will become here in this experiment. So the examples are
barium
roughly
titanate
solved.
as
Barium
our
titanate,
specimen,
etc.
as our ferroelectric ceramics. So it has a special types of structure. The structure is called perovskite structure. So it has AbO3 structure. So here barium is A, titanium is B, and O3. Okay, oxygen 3. So if you look at the structure, A is situated in the corners, in all 8 corners, and O is situated in the face centered, and in the center B is situated. Okay, so in this picture the structures is shown. So gray is barium, Ti is the black one, Ti is indicated as black, and white it is indicated as the oxygen in the picture. So in the application of an electric field, the displacement you can see from the picture. Okay, the perovskite structured materials, it has many applications. Now these are the apparatus that will be used in this experiment: a dielectric constant setup, a probe arrangement with RTD sensor. So this is the dielectric constant arrangement. So there are two probes, and one aluminum foil will be the connector of these two probes, and between these two probes our sample, that is barium titanate sample, the pellet, will be placed. So it will act as the capacitor, and this arrangement will be placed in a oven, and the RTD sensor will sense the temperature of the sample. Here is the complete panel diagram of the dielectric constant setup. So the oven is connected, the probe is connected through these probe terminals, and the RTD sensor is connected with this oven. Okay, and the oven is connected with the oven knob. Okay, so here two displays are there. One will display the temperature, which the RTD sensor uh, will indicate this temperature, and other is the capacitance meter. Okay, so this will show the capacitance of the dielectric material at that particular temperature, and one knob is there to set the particular temperature, to control the rate of the increase of the temperature of the oven. So we'll see the this setup in the live demonstration. Thank you.